So the main idea for this quest is to gain a better understanding of the concepts of projectile motion. So I'm going to quickly go through some of the concepts just to remind you what they are from the lecture before you start the activity. So a projectile is just a name for an object that moves under the influence of gravity in 2 dimensions, and its path is a parabola. And you can see there that ball that's bouncing, each of the paths shows a parabolic path. So the only acceleration that we're going to consider is gravity. We're going to ignore the fact that there's air resistance against the object. So if there's no air resistance, what happens is that the only acceleration is downwards. So if we were to drop a ball downwards, as we did in the last module, you know it goes faster and faster and faster as it falls, with an acceleration of 9.8 meters per second squared due to gravity. If there's no horizontal acceleration in the x direction, the x component of the velocity stays the same. So if we add a constant x component and an increasing y component, then we'll get a velocity that increases, and its direction is always a tangent to the direction of the parabola at a given point. So the speed in the x direction is constant because there's no acceleration in the x direction, and so the position in the x direction is just going to change linearly with time. But in the y direction, the velocity increases with time, and so the velocity is going to increase with time, and the position will increase as a square of the time. So if we launch an object in projectile motion, so that would be like throwing a ball, for example, it follows this parabolic path. And so usually when we start a problem, it'll tell us that we launch it with an initial velocity v0 at an angle of theta 0, either above or below the horizontal direction. And so the first thing we have to do is to break that initial velocity into a horizontal component, the initial x component, and a vertical component, the initial y component. And so we refer to these as Vy0 and Vx0, or sometimes you'll see it written as it is at the top here in these red equations, V0x and V0y. Those mean the same thing. So the first thing that we have to do is, when we solve a problem, is always break it up into components. And so if you look at the triangle there at the origin, you can see that the x component, the horizontal side, that side is touching, it's adjacent to the angle, so we're going to use cosine. So the x component of the initial velocity, Vx0 or V0x, is going to be V0 times cosine of theta 0. And the y component is the vertical side, it's opposite to the angle, and so we're going to say that it's a sine. So V0y is sine of theta times the magnitude of the initial velocity. So when we solve projectile motion problems, remember projectile motion is motion with constant acceleration that's always horizontal. So we can solve it by breaking it into 2 parts. We can solve for the horizontal motion. The velocity in the x direction is always the same. So if you know the initial velocity in the x direction, you know what it is at any point in time. And the position changes linearly with time. It's just the initial position plus the initial velocity in the x direction times time. In the vertical direction, then we use the equations that we had for free fall. And the only thing that we've done differently is we've put in Vy instead of just V like we had in the previous module. So Vy changes linearly with time, y changes quadratically with time, and we have that equation Vy squared equals V0 y squared minus 2g times y minus y0. We can also solve for the horizontal range, and the horizontal range is the distance that it travels in the x direction before it hits the ground. So we're going to solve for what is x at the point where y is equal to 0 in the trajectory. And if we do all the algebra, we can get the equation that r is equal to v0 squared, the initial velocity, the whole thing, not the x component or the y component, but the whole velocity squared divided by g, times the sine of twice the angle at which it's launched. And you can only use this equation if the object lands at the same height that it's launched from. If it takes off higher, so for example, you throw an object from the top of a building, then you can't use the range equation. But whenever you have a problem, like you kick a football from the ground and it lands on the ground, and it asks how far does it go, the easiest equation to use to solve that is the range equation. The range equation depends on the angle, and it's going to have its maximum value where the sine is 1. Remember, a sine function goes from -1 to +1, and the sine of 90 degrees is 1. So we want the argument 2 times theta 0 to be equal to 90, and so that's going to be at 45 degrees. So you can get maximum range when you throw a ball or you kick a ball or you launch a cannon, whatever you do, at an angle of 45 degrees. And at that location, the sine is going to be 1. So the range, the maximum range that you can throw or hit or launch anything, is the initial velocity squared divided by 9.8, which is g. And because the sine of 2 theta is double valued, there's always two angles at which you're going to get the same value for sine, and that's going to be at the angle of theta and 90 minus theta. So the two angles that add up to 90 are going to give you the same horizontal range. So 20 and 70, you can see in the picture, go the same distance. 30 and 60 go the same distance. If you had 10 and 80, those would go the same distance. So if the two angles add up to 90, then you're going to get the same range. So let's just go through a few concepts before I leave you with the activity for the day. So if you have a ball that's launched with an initial velocity shown there by the red arrow, when it's at point A, what's the direction of the acceleration going to be? So think about that for a few seconds. What's the direction of the acceleration at point A? So what's the answer? Well, the answer is the acceleration for projectile motion is just due to gravity, and gravity is always down. So at point A, the acceleration of the ball is just going to be straight downwards. Okay, so here's the next question. So the next question looks exactly the same. The only thing is it's asking what's the direction of the velocity at A as opposed to the acceleration at A. So again, so look at the answers. It's the same arrows. Which do you think is the correct answer? Okay, so what's going to happen? Well, what's going to happen is that as the ball goes along the trajectory, it's going to change its velocity direction so that it always stays tangent to the curve. So it's going to bend over a little bit further so that it is parallel to the curve at point A. So that's going to be path C. All right, next question. What's the direction of the acceleration at point B? So point B, what's the direction of the acceleration? Well, what happens? The acceleration is due to gravity. The acceleration is always straight down. So this question, be ready for a question like this on the test, where I ask you what's the direction of the velocity and what's the direction of the acceleration at different points on the trajectory. You should remember the acceleration due to gravity is always 9.8 and it's always straight down. Students tend to say that the acceleration is 0 at the top. If acceleration were 0, what that would mean is that everybody would go flying off the planet, right? There would be no acceleration of gravity holding people down. So if you threw a ball in the air and the acceleration magically turned off when that ball got to its highest point, that would mean that every time somebody threw a ball in the air or threw anything in the air, everybody would go flying off the planet every time that ball goes to the top. And that doesn't make any sense, right? So the acceleration is always the same no matter what point it is on the trajectory. It's always straight down and it's always equal to 9.8 meters per second squared. What does the velocity look like at point B? So remember what we said for the last velocity problem. What direction does the velocity go at any given point in that curve? Well, the answer is that velocity goes in the tangent direction to the curve, so the direction that that curve is at the instant it's at B, which is horizontally. Okay, how about point C? What's the direction of the acceleration at point C? Hopefully you're onto this right now. Acceleration is always down, right? So it's always going to be straight down, no matter where you are on the curve. And the velocity is going to be tangent to the curve. So it's got to be an arrow pointing in the direction of the curve at point C. So it's going to be diagonally downwards, like in point A. So remember to study these things. What direction is the velocity at any point in time? What direction is the acceleration at any point in time? Hint, acceleration is always equal to 9.8. It's always straight down no matter where you are in the curve. The velocity, the total velocity, always is tangent to the curve at any point in time. The x velocity is always the same at any point in time. And the y velocity is initially upwards. It goes to 0 at the point at which is at the very highest point, at point B there. And then it increases in a downwards direction as time goes on. So the quest today is going to be to play with the PhET projectile motion simulation, and there's a worksheet there. There's both a Word version of it or a PDF version, whichever way you want to fill it in. Complete it and upload the worksheet. So let me switch over to the simulation and just show you how it works. So here's a simulation. This is what it's going to look like when you load it. Over here in this top gray box, you can slide to change the diameter of the ball and its mass. And you can untick air resistance. So we're going to turn off air resistance. And then you can change the angle of the cannon firing by tilting it like this. And you can change the initial speed either by dragging over, or you can go up by 1 meter per second at any point in time by just clicking the arrows up and down. All right, so to fire, you hit the red fire button. You get a trajectory that's shown on here. You can use this thing and put it on any point there, and it'll tell you what the time is, what the range is, how far it's gone, and what the height is at that point in time. So we're going to play with that. And we're going to play with changing the angle, changing the speed, changing all the things, the mass, the diameter. We can put on the velocity vectors and acceleration vectors. So velocity vectors are green, acceleration is yellow. And if I launch the ball, you can see, let me put that into slow motion by ticking down at the bottom, and I'll launch it again. You can see acceleration, the yellow vector is always down. And let me replay it. The horizontal velocity, the green always stays the same, and the vertical one decreases, goes to 0, and then increases again as it goes down. You can clear the screen at any time by hitting the yellow eraser. All right, so go on, play with this, and hopefully it'll help you get a better understanding of how projectile motion depends on speed, acceleration, etc.